Good afternoon. I'm Peter. Welcome to my living room. I will be your host this afternoon for this session on mobility. And I would like to start with a short presentation on the future of intelligent mobility. The last 100 years, we've seen an evolution from horse-driven mobility to cars, and now the era of data is popping up in mobility. And you can see it in all these things on the streets. There's this concept developing that's called mobility as a service. It means that you no longer own your car or your bike, but you use services. You don't own anything, you just have a subscription. You can walk in the street and everything you see, you can use it. And at the end of the month, you'll get an invoice. So you can use a bus, a tram, you can use a bike, you can take a taxi, whatever. And as you don't own these vehicles are owned by another party that collects a lot of data on the vehicle and on you as a passenger. And that's also where all these guys are counting on for the future. We won't own most of our vehicles in the future, but we will use their services that generate data, and that data will then improve their services again. And there is actually a lot of cool stuff that we can do with this data and artificial intelligence. For example, in the field of logistics, there is this great concept called the physical internet. Internet is actually a digital infrastructure that combines packages from one side of the world, sends it to the other side of the world, and tries to encapsulate these packages as efficiently as possible. Now, some people would like to see the same with logistics. So if a company now sends a truck with its own products to the supermarket, they want the company just to send out all the products. They go to a distribution center. They get packaged together with a lot of other packages as efficiently as possible through big pipelines, to big trucks, or to a hyperloop. They go to another part of the country or another part of the world, and they get redistributed again, so they reach their final destination. So that's a cool thing that we can do if we have data about all these packages, the origins and the destinations. But we can also do very cool stuff with traffic lights. Currently, there's a project running in Flanders called Mobilidata. It's a 13 million project by the Flemish government, and it aims to digitalize a few hundreds of our traffic lights. So the traffic light controllers will be connected to the internet. This means that they will be able to connect to vehicles, to groups of cyclists, and the traffic lights will also be able to use data to better regulate their timings, so they can use more efficient the time they have to allow cyclists, pedestrians, and cars to continue their ways. Another great use of data and artificial intelligence is not only capturing what we do. There's this company, Sentience, from Antwerp, that does this. They use the sensors in your smartphone. They use data from the applications on your smartphone to know where you are going, on what means of transport you are, if you're biking or using the car. And they also use this data to predict what you are going to do, when you will go to work, when you will go to the gym, and what means of transport you will use. Well, this is actually really cool data, for example, to offer alternatives to people or to improve our mobility system on a large scale. If we can predict what most of the people will do in the next hour, we can change a lot of parameters to make it better. For the last decades, we also have been using a lot of data to forecast what infrastructure we will need in the future. We just count the number of cars today, we see what kind of economic growth we expect, and then we project into the future how many cars there will be more on our roads and how many lanes we need to add to our highways. And sadly, we can also use data to predict accidents. We can use data to predict how many children will die in traffic next year. But I hope you can sense that although there are a lot of cool things you can do with this data, there are a few problems. And for me, there are two big problems. And the first problem is the data itself. Because we're using data from sensors, from cameras, from IoT devices on our mobility system today. We use the data from smartphones, from GPS devices, from navigation software. But mobility today is not perfect. In the Brussels capital region alone, there's more than 11 square kilometers used for parking. So space that we can't use for anything else, we just let steel rest. And it's quite problematic if you know that the center of Brussels itself is only 4 square kilometers. Belgians, on average, they are wasting more time in traffic than they do exercise. Belgians waste about 100 hours a year waiting in traffic. And worldwide, every year, 7 million people, that's almost the entire population of Flanders, dies each year prematurely of air pollution. And then 3,200 people die in traffic every single day. So that's my first problem with using data. You can, of course, perfectly use data, and it's great data, but we should all be aware that if we use data from today, that today's mobility is far from perfect. So if you use it to make predictions of the future, be very well aware that you might create a future that's even less perfect than the situation today. And the second problem is about intelligence, about human intelligence. If we look at the last two examples I gave, for example, the infrastructure. Why do we want to predict how many cars will drive on our roads in 2030, for example? Does that mean that we see mobility as something outside of ourselves that just unfolds and we should just predict it and build more lanes to adapt to this mobility creature? Shouldn't we decide how many cars we want on our roads instead of predicting it and just building more roads? We could try policies to make traffic more efficient by putting more people in one car, by stimulating public transport. And I hope that everybody sees that we should not predict how many children will die in traffic next year. There should not be a single child that dies in traffic next year. And it's not that mobility is a beast outside of ourselves that just does what it wants. We are humans, we have brains, and we have policies to decide and to shape the future rather than to predict it. So my takeaways for today are: transport data is great. You can do absolutely great stuff with the transport data we have today. But if you use it, you should be aware that current mobility is quite crappy. And secondly, we do not really need to predict the future. We are humans. We have human intelligence. We should think about how we want the future to be, and we should shape the future. All right. Thank you for being here today. We will now move on to the next presentation, and I will come back at the end of the session for the Q&A. Thank you.
Good afternoon, everyone, and welcome to this 10-minute lecture about data science at the Port of Rotterdam. My name is Toby Tan, and I'm data scientist at Ordina. I'm happy to tell you something about better planning with ship arrival time predictions using machine learning. I hope you will enjoy. And maybe you already noticed the logos of Ordina and the Port of Rotterdam on the slides. Ordina is the company where I work for. It's the IT service provider in the Benelux for digital advantage. We have a wide range of IT professionalism, like data science, the business unit where I'm part of. I'm now hired for 2.5 years already at the Port of Rotterdam, Europe's largest seaport. Port of Rotterdam is also actively involved in several AI applications such as autonomous sailing, predictive maintenance, and calculating the estimated time of arrival of ships. About this last bullet point, this presentation will be about. Ordina helped the Port of Rotterdam developing the machine learning model that calculates the ETA, estimated time of arrival of ships. Why is ship arrival time predictor needed? ETAs are used in planning and optimization within a port. For example, berth utilization at terminals, planning of nautical services, will perishable cargo arrive on time, will a container be in a port on time to be loaded on the next ship. In all those cases, there is a certain planning, and the ETAs support parties to check if this planning will be reached, yes or no. At the moment, accurate ETAs are not readily available. So ETAs of shipping agents are assisting a ship during a port visit, and the ETAs of shipping agents often shortly before arrival, and also the accuracy of shipping agent ETAs varies. And so sometimes you see really good ETAs, but sometimes also you see very bad ones. So therefore, our solution is a ship arrival time predictor using machine learning. It calculates ETAs based on the ship's position and speed. ETAs are always up to date. ETAs are calculated as soon as a ship leaves a port, and the estimated time of arrivals are also available in the map application, also available through API for system integration. A very important enabler for our predictor is AIS, Automatic Identification System of ships. Each ship has a unique AIS transponder which sends out messages that are picked up by terrestrial and satellite receivers. And these AIS messages contain position data, speed data, course data, heading data, but also data about vessel characteristics and many more things like also destination, for example, of the ship. At the Port of Rotterdam, we have global AIS coverage. So if a ship sends out an AS message anywhere in the world, we can capture this. So this is a very useful data resource, as you can will learn on the next couple of slides. The predictor is called time to port, and time to port has two main steps. The first step is a path finding using graph analysis and graph theory. The second step is calculating travel time using machine learning. And in this first step, there's a graph-based network that determines the route to a port. It's like in your car navigation. You're now at this point, you want to go to your destination, and your car navigation will return you the shortest route, the fastest route, etc. Also, this graph network takes vessel dimensions into account. So if your ship is too large, for example, you may not pass certain fairways. The graph or map of seaways is inferred from AES data. So what we have done is plotting historical AES positions of ships, and this shows a density map of the world and reveals the true fairways of ships. Yeah, currently. Um, the second step is a machine learning model that calculates the time to port. A model is trained using millions of AES messages broadcasted by vessels that are already visited the port. The travel time calculated using AES-derived features. So here you see also the importance of AIS. First, we determine our graph network on it, and the second step is our input data for our model, and also you see AES-derived features, which are very important. Our model is a supervised machine learning model. In the training phase, we collect all historical AES messages, all historical AIS positions, and we check what the destinations at the point of time was of the ship. And we determine the route at that time, and also we collect the vessel characteristics at that time. Also, we know from the past what the actual travel time was in that situation, all those voyages, and together we combine this into a learning algorithm, and we construct a model, a machine learning model of it. Then in the prediction phase, for example, a ship leaves a port, it sends out an AES message. We gather this position, we check, okay, what's the destination of the ship? Then we calculate the route again, add some vessel characteristics, and this forms the input for our model, and our model will calculate the travel time. So this is how this predictor works in practice. The architecture behind the model is a clear distinction between the work of developer and the data scientist. In the past, when a data scientist at the Port of Rotterdam wanted to bring a model into production, we always needed help of the developer, and now we have given the data scientist full ownership on the process of training to eventually bring a model to production. So a data scientist is creating and retraining models for a specific port in Databricks. It's a cloud-based platform where you can write your Python code, but also your R code, Scala code, whatever you want. There's an automated pipeline that publishes models on AWS S3. Those models stored in AWS S3 buckets are being inserted into an AWS Lambda. We add some calculation intelligence to it and make it ready to be called by deployed applications. Developer writes application code whenever a deployed application needs an ETA prediction, then the AWS Lambda is called and the application can use an ETA prediction. Of course, there's you see here a clear distinction, but of course there's a continuously discussion between the developer and the data scientist about when to call a model, how to call a model, how to calculate inputs, which kind of inputs does the model need, etc. But this is now, let's say, our ideal setup to move forward. This is an example dashboard which makes use of the API. So here you see a list of ships, and now the Tomaros is selected. It's at the Mediterranean Sea at that time, because this is an old snapshot. This is a snapshot of February 2020. At that time, the Tomaros was heading to Rotterdam, as you can see in the third column. In the second last column, you see the time to port prediction. So that's the prediction that comes out of the API. And time to port predicts 207.7 hours for this Tomaros going from Mediterranean Sea to Rotterdam. And 207.7 hours is more or less 8.5 days. So this is really, let's say, the API in action, the API used by an application. And why AI in this case, and what did we learn? If we look at short-term prediction, there's our model behaves more or less like distance divided by speed ETA prediction. So in the short term, there's limited benefit. If we look at the long term, then our machine learning model outperforms the distance divided by speed ETA predictors, and the prediction error can be reduced by 20 to 50% depending on the prediction horizon. So that's pretty much. The lesson learned here is let data scientists take ownership of the entire process from training to the execution of the model. So that's more or less the architecture slide I've showed you. But this is in this setup, you're not interfering with the developer and they are not interfering with us. So that's for us a very good way to take our models into production. And that was my last slide. So thank you for your attention and have a good day.
Hi there, everybody. Welcome to my presentation on Classify and how to increase efficiency in processing orders. Now, we don't have a lot of time, so I'm going to skip straight to the good stuff. But before I can start talking about Classify, I first need to explain a different concept, namely IDP, or Intelligent Document Processing. Small spoiler, Classify is an IDP tool. Now, what is IDP exactly? Well, let me show you the definition right now, but let's go over some of the bold parts. Basically, IDP uses AI and machine learning technology to process unstructured data. Now, what is unstructured data exactly? Well, pretty much the opposite of an Excel file. In an Excel file, you have columns and you know exactly what type of data you can find inside these columns. Some of them might contain financial information, some of them might contain dates, some of them might contain names, etc. Now, processing structured data for computers is very easy. They've pretty much been doing this since the beginning of computers. But processing unstructured data has always been a huge hassle because unstructured data is unpredictable. So for the longest time, this has been a manual job, a human job, something that humans needed to do. Recently, thanks to advances in AI and machine learning, we are able to automate this task as well. And we do this in two different ways. First of all, we have categorization. You have all kinds of different documents and you want to divide them into categories. Orders are especially interesting to you, but you might not want your personal emails to be processed by your IDP tool, right? The second part is maybe more important, is extraction of relevant data. Pretty much what we do is we take, for instance, an order or any kind of document, right? An order could be a PDF, it could be a doc file, it could be an email, whatever. And then we extract all the relevant information. You want to know what company this order is coming from. You want to know what exactly they are ordering, how much they need to order from you, etc., etc. Now, automating these tasks solves a number of problems, right? We are talking about manual work. This is time-consuming work, especially in growing organizations. But most importantly, this is repetitive work. This is work that your employees most of the time do not enjoy doing. And because they get bored doing this repetitive work, it leads automatically to all kinds of human errors. And this leads to all kinds of issues further down the line. So we designed a product which is an IDP tool. But basically, before I start talking about Classify, I do need to share a dirty little secret that pretty much every machine learning-based tool has. Namely, that it requires training data in order to function. It's pretty much in the name, machine learning. So you need to feed it a lot of examples before it can actually start doing the job that you want of it. Now, typically, this is done in separate data gathering phases, right? Somebody will come to your company and it will and he or she will process your data in a way that is understandable for machine learning algorithms. Now, this is something that usually takes quite a bit of time, usually costs quite a bit of money. And we've noticed that this is an obstacle for especially smaller organizations that want to adopt artificial intelligence. So that is why we designed pretty much Classify from the ground up to tackle this problem. So if we take a look at some of the features that Classify has, if you look at the bottom row, These are features in black and white that you will find pretty much in every IDP tool. On one hand, you have our analysis. We have our statistics page that allows you to get all kinds of information on the processes that you are actually performing. And on the left side, you have the classification and extraction that I've mentioned earlier. Pretty much every IDP tool features this. But back to the problem of data gathering. Well, when we looked at this problem, we pretty much figured out that there is a very easy solution, well, somewhat easy solution to the data gathering problem, namely to integrate this data gathering phase into this IDP tool itself. And we do this in two different ways. On one hand, we have integration. Classify is a product which is very modifiable. We can pretty much adapt the user interface to any kind of environment that you are currently using, be it a cloud-based cloud-based web app, a independent desktop application, something that integrates with Microsoft Office, you name it. We integrate, we adapt Classify so your employees don't have to. And why do we do this? Well, pretty much Classify, when you first start using it, it does not have any AI or machine learning functionality at all. It is a document, unstructured data processing tool, which requires your employees to do the job manually, just like they've done before. We do add some, extra useful features like using shortcuts to label all kinds of different information. We use color coding to make sure that it is very clear what type of information has been extracted, what types of information might be missing. And this combines into a process that allows your employees to generate training data while using a tool that feels very, very familiar. But then perhaps most importantly, they are generating this training data, and in the background, a machine learning system is using this training data in order to start learning how to take over the job. So this is pretty much the unique selling proposition of Classify. So we have our effortless labeling tool that allows you to process any kind of document, emails, PDF files, Word files, even scanned images. They can very easily process these documents. And in the background, while they are processing these documents, a custom-built AI system is learning how to take over their job. Well, not completely take over their job. I'm going to explain a bit more on that later. But this means that it is a fully integrated environment that is very easy for your employees to use, which means that Classify can start generating value from day one. Right? The moment your employees start using this tool, thanks to things like shortcuts and color coding, you'll already notice some small efficiency gains. But as time goes on, you'll notice that more and more of their repetitive work is being taken care of by Classify. We do have all kinds of additional features. I don't have the time to go over them all, but we are especially proud of our modular AI approach. Classify was built by BrainJar, as you might notice on my shirt here. We are an AI company, and we know that AI is moving at a breakneck pace. So we designed Classify from the ground up in order to have AI models that are very easily replaced by newer versions, allowing you to get increased efficiency without requiring additional training data, which is a very interesting feature. Now, please feel free to take a look at some of the other features as well. They are all very interesting, but time forces me to move on. Using Classify, accepting Classify into your organization is a very easy 7-step process. It starts out with an intake conversation. Pretty much, we will find out exactly how your organization works, how to integrate Classify into your existing infrastructure. Then we will, actually integrate Classify, modify the user interface so that it feels natural for your employees. And then pretty much in the beginning, it's business as usual. Your employees start using this tool. It doesn't feel that different to what they've been using before. It's slightly more efficiently, but in the background, we are gathering training data in order to train a machine learning system to start gradually taking over some of the repetitive work. More and more of their time will be freed up. But of course, a machine learning system is not perfect. They still need to check the work of the machine learning system. And sometimes there might be a mistake, right? But if they correct this mistake using our, unified labeling interface, they can very easily correct this mistake and then retrain the machine learning algorithm to do a better job in the future. And then all that remains is to analyze and see how much time and money you are actually saving. And calculating the amount of money that you are saving is actually quite easy. Simply take a task that is performed by an employee, take 80% of that time, multiply that by the task frequency, pretty much how many times a week or a month that your employee has to do that job, multiply that by the amount of employees that are actually doing the job, multiply that by their wages, and multiply that by our product lifespan, which we estimate to be at least 10 years thanks to our modular AI approach. We can pretty much guarantee that the end number that you get is going to be way bigger than the cost that you would actually need to spend on Classify. And it's not only about the cost, because as research has shown, reducing the amount of time that your employees need to spend on repetitive tasks vastly increases the amount of time that they can spend on value-adding tasks. So that's pretty much it for me. If you have any further questions, do not hesitate to contact us. And one of the possible ways on the left, simply go to tom.classif.ai and schedule a meeting with one of my partners. Thank you very much for listening.
Hello, everyone. My name is Michiel Vlaming, and I'm a postdoctoral researcher at the Image Processing and Interpretation Research Group of Ghent University, which is also a member of IMEC. And I'm also affiliated to the UAV Research Center of Ghent University, which was established at the end of last year. So I will tell you a bit more about the work that I'm doing on aerial inspection of PV power plants using multimodal image data fusion. So this work was conducted in the ICON project Annalys PV, together with the partners Sitemark and NG Laboralec. So the problem that we want to solve is the one of PV power plants that need to be regularly inspected for anomalies or degradation, which usually takes a lot of time, and time is money, of course. So what we want to develop is an automatic defect quantification system that is using drone-based imagery, as you can see on the image. So what we notice is that many of the defects in PV power plants, that they actually provoke an increase of temperature. So as you can see on the image on the right, so for example, if there is an issue with the junction box, then typically it will appear as a hotspot in a thermal image. So for that reason, we integrated thermal images in our solution. But what we also notice is that that even though we can easily detect hotspots in thermal images, the source of the anomaly is usually better visible or better noticeable in the RGB image. So, for example, the image here, we can more easily see that probably there is some vegetation growing on the solar panel, or perhaps there is a soiling, or the hotspot is induced because of shading or corrosion of the material, or it can even be due to snail trails or even bird poo. So now I will explain the general approach that we followed. So first we developed a technique to align or register the thermal images on top of the RGB images, as you can see here on the left image. And after that, we first normalize the thermal images, because sometimes it can happen that that the intensity values of the thermal image is not everywhere the same for solar panels which are not damaged. But we want that if a solar panel is okay, that they all have the same intensity in the thermal image. And sometimes, because of sun reflections, this is not always the case. So we want to normalize the thermal images. So the third step is then the actual detection of solar panels, as you can see here on this image. And finally, we want to detect and classify the anomalies that are occurring within a solar panel, or sometimes also inter solar panels. So now I want to dive a bit deeper in the problem of solar panel detection. And actually for this, we developed two different methods. So the first one was some kind of classical machine learning approach. So we start with several pre-processing operations on the thermal image to enhance the contrast and to make the borders of the solar panels more salient. So we conduct a gamma correction and some morphological operations. And then we see that it is more easy to extract the contours. And those contours, we will evaluate them for shape and size. And after that, we will compute texture descriptors for those patches and then train a support vector machine. And what you see here on this image on the right is the output of our support vector machine that we trained. And sorry, even though the results were already quite satisfying, we tried to do better. So we also tried to use deep learning for that. And actually, we used the annotations that we obtained by the classical approach to train the neural network. Well, actually, we first visually inspected them, and the correct ones we used to train the network. So our method is based on the MaskR-CNN network. And well, if we consider this thermal image here, then one of the results that we obtain is the image on top of that. And as you can see, the method is performing quite well. But sometimes, so again, because of sun reflections, some areas or some solar panels are slightly more difficult to detect, such as the one here. But most of the time, the sun reflections do not induce too many problems. But more problems occur when there are shadows casted, for example, from above power lines. So as you can see here, they induce some lines on top of the solar panels, and as you can see, our deep learning method has quite some problems with that. And finally, it can also happen that some structures in the scene are very similar to solar panels, as you can see here, and then they will also be detected as being solar panels. Now, to deal with this, we try to also detect entire strings or modules of panels, and we use this as kind of prior information to predict where missing panels might occur. So what you see here on this image is a mask indicating where solar panels are present, and with our own eyes, we can easily distinguish that something is missing here. So what we did is we actually draw the grid of solar panels, and then we checked if every cell of that grid was a true solar panel. Of course, it doesn't mean because there is no solar panel detected that there is a misdetection, because sometimes it can happen that the solar panel is just missing, which is then an anomaly. So if we now combine our deep learning method with this kind of post-processing step, then we see that, well, in this case here, the solar panel that remained undetected is now detected. Same for the image with the power lines or the shadows from the power lines. We can see that now, well, quite all of the solar panels are detected. And for the last example, we see that the panel-like structures, they are no longer detected because they do not appear in a regular, or they do not appear within a string of solar panels that were detected, or actually not detected. So if we also try to quantify the results a bit, then we see that if we simply apply the neural network, then we achieve a precision of 99.5%. So this means that from all of the solar panels that our system detects, 99.5% of them are true solar panels. And the recall is 94.9%. For this precision. So this means that from all of the solar panels that are present in the scene, we detect 94.9% of them. And now if we combine it with our post-processing step, then we see that we can actually, for a slight increased precision, we can actually increase the recall a lot. So by so instead of 94.9%, we can increase it to 98.1%. which is actually a quite good result. So now the last step, or the fourth step in our method, is the actual detection of the anomalies using the thermal images. And for that, we devised the semi-supervised learning approach. So first, we tried the classical segmentation method on the image that contains the solar panel, because once we detected the solar panels, we can easily extract just that image patch from the image. And yeah, we actually executed the SLIC segmentation method. So it's a segmentation which will divide the image in superpixels, as you can see here. And what we do then is we simply pick the SLIC segment with the highest intensity, or multiple segments, as you can see here. And again, this method is performing quite well. But as we always want to do better, we feeded those images that we again visually inspected. We feeded them in a mask RCNN neural network. And I also have to mention that we again try to enhance the contrast in the image. So we actually feed it some kind of augmented image. And what you can see here, these three images are simply three examples of hotspots that are detected. And we can actually conclude that our method is able to achieve a recall of 95.5%. So it means that from all of the anomalies that are present, our method detects 95.5% of the cases. So of course, we want to also go a bit further and not only detect them, but also classify those anomalies somehow. And as you can see, there are several types of anomalies. I only listed a few of them here. So a single hotspot, which can be induced by several different sources, as I explained in the beginning. But it can also be a bypass substring, as you can see here. So a bypass substring is typically like 1/3 of the solar panel, which is cut off or is defect. And it can also be a double bypass substring, which means that 2/3 of the panel is actually defect or disconnected. So in the end, we use at this moment 8 different data sets with different specifications. Below here, you can see the total anomalies that we are using for that. And you notice that actually our data set is quite imbalanced. So these diode issues or junction box issues, they do not frequently occur because, they simply do not frequently occur in reality. So for that reason, we try to tackle this class imbalance by using all kinds of different data augmentation techniques. So we add random contrast or brightness. We take crops of the images or we rotate them in order to make sure that we have enough samples of those cases as well. But it remains a difficult problem because many of these issues, for example, with the junction box or a diode, appear as some kind of hotspot in the image, but they have they are slightly different in shape and also in the position where they occur on the solar panel. But this thing is still ongoing work, so we also want to combine it with the RGB images, of course, to also be able to indicate the source of the anomaly. So in conclusion, in the end, we managed to build a solar panel detection, which is very reliable. And regarding the detection and classification of anomalies, the detection itself is also very reliable. And the things that we will work on the future is to have a more precise classification of them, and also we will try to include the source of the anomaly in the training process as well. So this concludes my presentation. So thank you for listening. And if you would have any questions, then feel free to ask. So thank you.
Hello, my name is Raphael Hoostetler, and thank you so much for spending the next 10 minutes with me, and I really try to make it worth your while. I'm going to be talking about instant mobility with humanoid robots and VR gear. I'm the founder of the company behind this humanoid robot, Roboy, that you're seeing here, which is called Devantro. And
Let's just dive right into it. So in the last few weeks and months, I'm sure you have been receiving memes like this, where experts recommend keeping your daily rituals even when working from home, or work from home archaeologists, work from home surgeons, work from home lifeguards, or work from home construction workers. While we love these memes and they're certainly very funny, they also highlight one of the bigger problems that this pandemic has sort of unearthed, and that's one of the problem of traveling. We're traveling every day, and we're so used to it, we don't think so much. So let's have a quick analysis of why we actually travel. First, it's connection. It's connection to our loved ones, to places and cities, to the nature, to history, to peers that we work with, but also to the most important moments of our lives. And the other big reason is work. Basically, we go to work because we have heavy and difficult to use our equipment. We have big materials. Our work is actually being physically there, or at the end of the day, it's for forming these connections, but in the work context. And work from home actually only is able to sort of solve for this last instance. All of the other instances we cannot solve for. And this is a major part of our industry. And that's one of the reasons that the worldwide travel industry is about $9 trillion US. And they're currently bleeding money because of this disruption that no one was foreseeing. And if we think about it, there also has been a small sort of positive to it. And that's travel is actually extremely resource wasteful. It's inefficient. We haven't solved for good mobility for personal travel. And if you look at the innovation that has been happening in this space in the last year, it has been, well, marginal optimization. For example, if we look at Uber, it's a multi-billion US dollar business. And what they've done is basically making it a bit more comfortable to call a taxi. And even with upcoming disruptors, such as autonomous cars, which will just make it more relaxed and comfortable to travel, and flying taxis, which will make it faster, we basically don't solve for the big problem society has today. We don't solve for sustainability. And there's one upcoming technology, though, that does solve for this, and that is going to disrupt all these previous technologies, and it's called telepresence. So it became possible, this technology, and I'm going to talk about what it is in a minute, because we're seeing convergence in technical development. First, connectivity has become ubiquitous. Basically, we have high bandwidth, low latency, high reliability connectivity almost everywhere now. So that means we can transmit a lot of data very fast between two places. And of course, ideally, this is all our senses, all we see, hear, experience, so we can be at a different place. The second part is AI as a tool. We're using AI and robotics at all the places. It's part of our control algorithms, it's part of our vision algorithms, it's part of our data processing, and so on. So really, this is a tool that we're using at many different places. And the last part is sort of really getting from robots that live in the lab space to robust robots. And this is truly a game changer, because if you look at sort of our capability of being present remotely so far, it basically started with the phone. And the phone gave you the opportunity to transfer your voice and your hearing to a different place, but you have no control over what's happening at this place with these two things. So basically, if someone is listening to you or not, you don't have any control over that. You also can't decide where exactly you're listening or where you're positioning it. So you don't have any way of active sensing. Zoom, it just basically added the visual part to it and made it easier to connect several people together doing this. But again, you don't have any agency over the place where you connect to. You can't do anything at the location. And for a few years, what we've been seeing is basically Zoom on wheels, which gives you the opportunity to move around in the remote place, to decide on what you're looking at, decide where you're hearing is, but no sort of interaction with this place. You can't manipulate anything. You can't take up anything. You can't do any physical work at this place. And this is really the game-changing last part that is missing. Having physical interaction at a remote place is what's been missing in the last years, so we can truly transport a person or teleport a person into a robot so they can do work or can interact with the world in a remote place. And there's a very big competition that we're also competing in that sort of summarizes this, I think, in a very succinct way.
We had internet, we had iPhones, now we'll have avatars.
The ANA Avatar X Prize is a $10 million competition that challenges teams to develop a physical robotic avatar system that can transport your senses, actions, and presence to a remote location in real time and feel as if you're actually there.
We'll be able to completely break through all of the barriers of distance, time, and cultures that exist in our world. I think that will allow us to unleash the full potential of humanity for the very first time.
So telepresence truly detaches work from location of the worker for the first time. And this is done by having a humanoid robot that you are connected to, wearing an operator suit. And the robot basically copies your motion. So if you move your head, the robot moves his head. You are seeing what the robot is seeing. You're hearing what the robot is hearing. If you're speaking, it's being heard on the other side as if this was you. And if the robot is being touched, you feel this. So you feel the forces that are being transmitted to the robot. So for you, it's as if your whole body has been transported into the robot. And this has many use cases. For example, sick children going to school can now stay sort of with their peer groups and still be with their friends. And that's actually a huge change. And there was several of these studies being done, and it has been shown that this made a lot of a difference for these children. On a more industrial note, this is a great way of bringing manual work to places which are either remote and hard to reach or dangerous. And having sort of remote manipulation capabilities at these places can be a gigantic cost saver, because it means that, for example, in oil rigs, you wouldn't need any you wouldn't need any people anymore. You could all do all the work with robots that are being telecontrolled. And finally, and I think it's one of the most important use cases, is in care. So we are already looking at significant shortcomings in care workers. Our society is aging. We do need a lot of we need solutions for this problem. And one of the main thing is that if you look at the day of an elderly person, they don't need care all the time, but at very specific points in time. And that's why having a robot there that is being teleoperated from time to time is actually creating a huge value, because it dispatches it sort of removes the necessity of travel from the nurse. So you can be jump from patient to patient really quickly and solve their local problems and look after them, having more time for the interaction that matter. And of course, if you have a CEO that wants to show the world how innovative they are, having a speech at all the locations in the world together at the same time is a great way of obtaining an audience. And let me show you how this looks.
However, we have been very actively using the last few months and made huge progress, because if you're looking to your left, what you're seeing is that this is no longer Roboy being Roboy, but it's actually Raphael being Roboy. So I can see what Roboy sees, I can hear what Roboy hears, and because it's tracking my head, it truly feels for me like I'm sitting 1 meter to the left.
And also, we've made huge progress in controlling the robot. This is what you're seeing here. Basically, the robot is copying the motion of the controller. So it's moving the arm where the arm is going. And these were first motion experiments that we've been doing in the last few weeks. And one big difference, though, of being a robot is that you don't necessarily have to have this, only the senses that we humans have. So we can augment the perception of a human. This can mean that we can make the pulse of a patient visible. It can mean that we can show infrared images, and sort of, if you're at the remote site, you immediately see temperature hotspots. We can use microphone arrays as a sound camera, so to speak, that let you see where sound is coming from. And as you see in the last picture, this can be a very important tool, for example, to detect gas leaks. And of course, having a robot detect the gas leak is a lot safer than having a worker do it. So as you see, telepresence is an upcoming technology. It's nothing that is sort of there off the shelf yet. It's sort of coming to society right now. We are looking for use cases, so let us know if you have ideas. And before I end, let me sort of give you a quick view of what it could mean if we had instant travel. You could wake up in the morning in your cottage in the mountains, and instead of traveling for 2 hours to work, you jump into your operator suit, you work on the oil rig, you do the hard work, which is easy because, of course, the robot has an augmented strength compared to you. And in lunchtime, you get the time to visit your elderly parents, which are living a few hundred kilometers away, look after them, see if they're fine, and all that, be back for the amazing sunset in the evening. I think this is really a vision worth living for, and all of that is being fully sustainable. It is tremendously reducing the amount of the impact this has on our planet, because not traveling means also not spending the energy. And so basically, I can only ask you, let's teleport to shape a sustainable world. I think this is your chance to lead the change. If you're interested to work with us to explore what it could mean and where these use cases could be applied in your company, we would love to learn more. Please go to robo.org/start. And we're really looking forward to take the discussions from there. Thank you so much.
Welcome in the broadcasting centrum of this conversation, and we will move on with a small Q&A session of about 10 minutes when we will switch back to the next session. If you want to stay more for a little bit more of Q&A, you can stay in the Zoom session or watch it afterward. Let's start with a question for Toby. We got through the YouTube question channel. Toby was giving an interesting presentation on the Port of Rotterdam. And the first question we got was from Bruno. He says that sea lanes are recently well known and defined, especially for the North Sea. So he's asking himself why we should infer sea lanes from AIS data. Toby?
Yes, thanks Bruno for that question. Okay, yeah, so the sea lanes are indeed well known and defined, I agree. However, from a technical perspective, we need the nodes and edges of this network. And a couple of parties offer this network on the market, but we decided to develop it in-house. But therefore, we needed this global AIS data that we already have in-house to reveal the historical ship position and start determining sea lanes ourselves. So more, So if you open a map, you can see some application already the sea lanes, but it's more from a technical perspective.
All right, thank you, Toby. Let's move to David from the second presentation. He was giving an interesting presentation, an enthusiast presentation, and sharing some dirty secrets on Classified IA on document processing. David, I've been working for a city, and we've been sending CCTV images to companies to have the numbers of cars counted. I also have an accountancy program where my incoming invoices are so-called analyzed by AI programs, but I've heard of stories where they send these images or these CCTV footage to faraway countries, and they have people or low-paid people do the work. When can I say that something was done by an algorithm or by a person? Do you have some little secret on that for me as well?
Well, I would say that the secret is if they promise you 100% automation, then they're pretty much sending your access data to India whenever there's an edge case. So that's one way to tell. Basically, we design Classify. We always say to our clients, like, okay, there's always going to be a manual check. You will always need to do, especially for important stuff like subsidy or important orders, you always need to do this manual check. Machine learning does have an error percentage. Additionally, our software is completely open source, so it runs offline in a sandboxed environment as well. So if you're especially paranoid, you could just put it somewhere where no internet will ever access it, and then you will be very sure as well.
All right, very cool. Thanks for the tip. We'll go to Michiel, who gave the third presentation, which was very interesting, and how image processing can help us detect faulty solar panels. I was wondering, Michiel, because I assume you are using drone images now. I was wondering, as quality images we are getting quality images from satellites, if we can use these images for your application, because that would potentially mean you have a multi-million-dollar business model, because you could proactively go and notify companies when their solar panels aren't working well. Is that a correct assumption?
It is correct. So in theory, that should be possible, but I see two main issues. So first of all, we are relying on thermal data for the most part. And so thermal data is captured in the near infrared. So I'm not sure if the specifications will be the same if we sense from, or if we use the satellite data compared to drone data, because the ambient temperature is different, of course, if you capture it from a drone or from a lot higher. So I think so I'm not sure how the data looks, so I should have a look at that. And the second thing is that the resolution should, of course, also be high enough in order for the algorithm to detect it. But in theory, it should be possible, and then it would be a nice use case indeed, because you can actually use all of the data in a semi-supervised learning way, so that that we don't need to annotate all of that data. If we just annotate our own data, then it should be able to learn itself by data that it has never been annotated. So it's an interesting use case, yes, for sure.
Okay, thank you. I hope you can make a lot of money with it and make a lot of people happy. And then we'll move on with a question for the last speaker. It's Raphael from RoboAvatar. Thank you for this great presentation. It was the first time I heard of the concept. We also got some questions in the YouTube channel. For example, from Bruno. So he says, for example, if I take the healthcare use case, this would mean a robot in each elderly house in order that the nurse can switch from patient to patient. What would the robot do the rest of the day?
So it's a great question, and of course, like at some point we want these robots to be autonomous, and we require sort of human help or telepresence as little as possible. And like already today, they could be doing some simple tasks like surveillance or being able to connect to someone if they want to speak to someone, or other like simpler things that you could do autonomously. So the telepresence is really necessary for the complex interactions, like putting on, like when the robot actually has to touch the human, for example. We are years away of making this autonomous.
Okay, thank you. I was also wondering, Raphael, when you talked about the nursery or the elderly homes, you're not actually deploying a robot, you're putting a person inside of a robot. Is there a line somewhere between a robot and telepresence, and where is that line? And does it make a difference for the patients, for example?
So I think the main difference, like I think any good telepresence robot is also a good robot, but not every good robot is also good for telepresence, because in telepresence we very much rely on the human morphology, and we are very good as humans in using our morphology. So where my hands are, that this is sort of the setup of our bodies, and so there the line is sort of swimming, because you can, of course, if the robot is capable enough, you can switch it to autonomous task and let it do autonomous tasks if it's good enough doing that. But there's a lot of research that shows that we are more comfortable around humanoid robots, or with have more or less human morphology, because we kind of know what to expect. Like we have a very good idea of how humans are moving and behaving. And even there's also like research that shows if you work with an industrial robot arm, it will be more efficient working together with a person if that robot arm uses a mostly human-like trajectory. So if the robot, if it gives you something, passes you something like this, that's because it's more natural than it's something like this, which is weird because you cannot pre-compute this, or you don't expect this trajectory. So from that sense, these humanoid robots they're more complex, so that's a pricing question at the end of the day as well. But we believe that they yield superior like service quality.
All right, good, thank you. Then we'll move back to the previous presentations. So Michiel, on the solar panels, it looks great for solar panels, but have you also tried, or is it easy to change or use the algorithm, for example, for leaking air conditioning installations, or when the isolation on the roof is not working well? Would it easy to change the algorithm for slightly different use cases?
Well, it's not too difficult, but we should retrain the network, of course. And then again, the same problems occur in the sense that we need enough training data. So people need to annotate some samples at least. But in theory, it's possible, yes.
Okay, great. Thank you. And another question for David from Classif IA on the automatic document processing. David, I really liked your enthusiasm, and it sparks a lot, but I was wondering, can you mention the coolest use case or some of the coolest use case that I can do with your software, because it wasn't really clear to me how I should use it?
Yeah, so basically Classify, I don't want to say, is a very boring tool using very interesting technology, is what I always say. So we use that for transport orders. We use that for billing, which is the run-of-the-mill stuff that pretty much everybody associates with IDP. But internally, we've also done some testing using on social listening, basically social media channels, and then classifying and extracting the most important elements from social media comments. Especially in very big corporations, this is a huge problem. And we've also had one CEO ask us, so I did mention those classifying personal emails and then not processing those personal emails. Well, we had a question asking if we could actually do that, answer mails from the wife automatically, but unfortunately you would probably need some kind of chatbot solution for that as well.
All right, thank you. So I'll just finish with one more question for Toby. So you all had two questions. It's the second question that was asked on YouTube, Toby. Somebody was asking, how do you tackle the changing importance of accuracy over time? Because at some moments in time, accuracy is more important than at other moments.
Yeah. The higher the prediction horizon, the harder to reach a higher accuracy, I would say. But by talking to several parties that we could support in the planning with this predictor, we learned that predictions of 14 days or less were sufficient. Therefore, we included several features that can support such a long-term predictions. And on the other side, we indeed excluded voyages in the training where the ship was too close to the port, because those voyages are less important, and we want to avoid some noise in our prediction.
Okay, I think it was really cool to hear that you can predict the time for a ship, even when it's still in the Mediterranean and it still has to sail a lot of time. So thank you guys, thank all of you for the great presentations and for the answers, and I'm looking forward to hear a lot more about what you're doing and seeing you in the news with your great applications.
Thank you so much.
Thank you, Peter.
Have a great afternoon.
You too. Bye-bye.
You too. Bye-bye.
Bye.
Bye.